Welcome to Part 7 of Applied Chemistry, where we will discuss knocking, octane number, cetane number, and their significance in fuel and engine performance. This section will explain how these concepts affect engine efficiency and how different fuels are rated for optimal use. In this section, we will discuss knocking, which is a critical factor affecting the performance of internal combustion engines. Knocking, also known as engine knock or detonation, is an undesirable occurrence in internal combustion engines. It happens when the air-fuel mixture inside the cylinder ignites prematurely or unevenly, leading to abnormal combustion. This can cause engine damage and loss of performance. There are two main causes of knocking. Pre-ignition. This occurs when the fuel-air mixture ignites before the spark plug fires, often due to hot spots in the engine cylinder, like carbon deposits. Auto-ignition. When the unburned portion of the fuel-air mixture ignites due to the increased pressure and temperature during combustion, it results in uncontrolled explosions, disrupting smooth combustion. Knocking can have severe effects, including engine damage. It generates high-pressure pulses that can damage engine components like pistons, valves, and cylinder walls. Loss of power. Knocking reduces engine efficiency, leading to noticeable power loss. Increased fuel consumption. The irregular combustion results in incomplete fuel burning, causing higher fuel consumption. The octane number, or octane rating, is a measure of a fuel's ability to resist knocking during combustion in a gasoline engine. The octane number is a measure of a fuel's ability to resist knocking. It is determined by comparing the fuel to a mixture of isooctane, which resists knocking and is assigned an octane number of 100, and N-heptane, which knocks easily, and is assigned an octane number of 0. There are three main types of octane ratings. Research octane number, RON, measured under mild conditions to simulate low-speed driving. Motor octane number, MON, measured under more severe conditions to simulate high-speed or high-load driving. Anti-knock index, aka the average of RON and MON, typically displayed at fuel stations, aka equals RON plus MON whole divided by 2. Why is the octane number important? Preventing knocking. Higher octane fuels are more resistant to knocking, which ensures smoother engine performance. Engine performance. High-performance engines, especially those with turbochargers, require high-octane fuel to prevent knocking and allow the engine to produce more power. Fuel efficiency. Using the right octane fuel optimizes engine efficiency, reducing both fuel consumption and emissions. Premium gasoline typically has a higher octane number, around 91 to 98, than regular gasoline, which is usually around 87. While the octane number is relevant for gasoline engines, the cetane number is used to rate diesel fuel. The cetane number measures the ignition quality of diesel fuel. It is based on a comparison between cetane, which ignites easily and has a cetane number of 100, and isocetane, which resists ignition and has a cetane number of 15. Diesel fuels with higher cetane numbers ignite more easily and provide smoother engine operation. Here's why the cetane number matters. Ignition delay. The cetane number reflects the time between fuel injection and combustion. A higher cetane number means shorter ignition delay, resulting in smoother and quieter operation. Cold starting. High cetane fuels perform better in cold conditions, making it easier to start the engine in low temperatures. Engine efficiency. Diesel engines running on high cetane fuel have improved combustion efficiency, which enhances fuel economy and reduces emissions. Most diesel fuels have a cetane number between 40 and 55. High-performance diesel engines, such as those in marine or railway applications, require fuel with cetane numbers closer to 55 or higher. The chemical structure of fuels affects their performance. For octane number, Branched hydrocarbons like isooctane and aromatic compounds have higher octane numbers, making them more resistant to knocking. On the other hand, straight-chain alkanes like N-heptane tend to knock easily and have lower octane numbers. For cetane number, straight-chain hydrocarbons like cetane have high cetane numbers because they ignite easily. Branched hydrocarbons and aromatic compounds have lower cetane numbers, meaning they resist ignition. In summary, knocking occurs when the air-fuel mixture ignites prematurely or unevenly, leading to inefficient combustion and potential engine damage. The octane number measures a gasoline fuel's resistance to knocking, with higher numbers providing better performance in high-compression engines. The cetane number measures a diesel fuel's ignition quality, with higher cetane numbers leading to smoother engine performance and shorter ignition delays. Both octane and cetane numbers are critical for optimizing fuel performance and ensuring efficient, reliable engine operation. We've reached the end of our detailed exploration and covered different topics in this video. Thank you for watching, and don't forget to like and subscribe for more tutorials on applied chemistry and other exciting topics.